Hello students, welcome to the organic chemistry class. In this video, we'll start with the very first unit of your organic chemistry paper code 107, that is structure and bonding. The very first topic in this is bond parameters. We all know that the characteristics of a bond are bond length, bond energy, and bond angles, which are known as these characteristics of a bond are known as the bond parameters. We'll discuss these parameters one by one. Let us start with bond length. In a molecule, the atoms, they are always in a vibration mode. वो आपस में vibrate करते रहते हैं with respect to each other. Or due to this vibration, there is no fixed distance between the nuclei of the two atoms. दोनों atoms के बीच में कोई fixed distance नहीं होता और इस कारण से किसी भी मॉलिक्यूल में bond length निकालना मुश्किल हो जाता है. Even then, we define bond length as the average distance between the two nuclei of bonded atoms. किसी भी मॉलिक्यूल में जो दो बॉन्डेड एटम्स हैं उनके बीच का एवरेज डिस्टेंस बॉन्ड लेंथ कहते हैं. इस बॉन्ड लेंथ को निकालने के लिए देयर आर वेरियस मेथड्स सच एज एक्स-रे, न्यूट्रॉन डिफ्रेक्शन मेथड, electron diffraction method, molecular spectral method, electronegativity methods, etc. Let us see how bond length can be determined. Suppose we have a molecule AA, that is A2. Molecule is A2, the bond is AA, and let us say that the bond length is DAA. Then, and the radius of the atom A is RA. So the covalent radius DAA, this is equal to 2RA, that is the sum of radius of the two atoms. If the electronegativity difference between, suppose we have a molecule in which the two atoms are different, a heteroatomic molecule, let it be AB. If the electronegativity difference between the two molecule AB, that is XA minus XB, is very small, then the bond length DAB is equal to the sum of covalent radius of the two atoms A and B, that is RA plus RB. RA is the radius of atom A and RB is the radius of atom B. In case the electronegativity difference between the two atoms is large, XA minus XB is large, then the bond length DAB, it is given by Shoemaker-Stevenson's equation, that is DAA is equal to RA plus RB minus 0.09 XA minus XB. This is the electronegativity difference, and RA is the radius of atom A and RB is the radius of atom B, which is given in the units angstroms. For ionic radius, the bond length is given by the radius of cation plus the radius of anion. For your reference, the bond lengths of some common diatomic molecules are given, like hydrogen HH, the bond length is 0.71. This you can study how the bond length varies with the size of the atom and the number of bonds. Now let us discuss the various factors affecting the bond length. It should be noted that the value given in the above table do not hold good for all the compounds. The values which we have given in the table in the previous slide, they do not match with the experimental values. because bond length is not simply addition of ionic or covalent radii. Why they do not match? Because here we just theoretically study about the addition. We add up the ionic or the covalent radii of the concerned atoms, but there are various factors that affect the bond length. So let us discuss all these factors one by one. First, electronegativity. The very first factor is electronegativity. You all know what is electronegativity. Electronegativity is the tendency to attract electrons towards itself and attain a negative charge. According this factor, we have already studied this equation. Shoemaker and Stevenson's equations earlier we have given that if the electronegativity difference between the two heteroatoms is large, then the bond length DAA is given by the sum of the radius minus 0.09, the electronegativity difference. The next factor is the bond order. Bond order, you all know that it is the number of bonds. Number of bonds, if the number of bonds are large, bond order will be large. If the number of bonds is less, bond order will be less. For example, Cl, the bond number of bonds is 1, so bond order is 1. O double bond O, number of bonds is 2, so bond order is 2. This bond length is inversely proportional to bond order. Greater the bond order, smaller will be the bond length, and smaller the bond order, greater will be the bond length. For example, carbon single bond carbon, the bond length is 1.543 angstroms, whereas carbon double bond carbon, the bond order has increased from 1 to 2. The bond length decreases to 1.3. And carbon triple bond carbon, here bond order again has increased. The bond length decreases to 1.2 angstroms. Carbon single bond nitrogen, the bond length is 1.47 angstrom. Carbon double bond nitrogen, it is 1.28. You can see the difference. By the increase in bond order, the bond length has decreased from 1.47 to 1.28 angstroms. And carbon triple bond nitrogen, the bond length further decreases to 1.15 angstrom. The next factor that affects the bond length is hybridization. Bond length decreases with the increase in the percentage S character of the hybrid orbitals. Percentage S character, you all know how it is calculated in the hybridization, say sp3 hybridization. There is one S orbital and 3 p orbital. So the number of S orbitals is 1 out of the total 4. It is 25% S character. Here in sp2 hybridization, it is 1 out of 3. Percentage S character is 33.3. In sp it is 50. So as the percentage S character increases, the bond length that decreases from 1.093 to 1.057, and carbon-carbon bond length also decreases from 1.54 to 1.20. This we are considering in the molecule ethane, ethene and ethyne. The last factor that affects the bond length is resonance. Resonance, you all know that when a number of structures, electronic structures, Lewis structures or electronic structures are drawn to explain all the properties. In resonance, a very common example is of benzene. Benzene molecule, the carbon-carbon bond length, here it is a double bond. This one is a single bond. This is single double. So all the bonds have both single and double bond character. The carbon single bond carbon bond length is 1.43 and carbon double bond carbon is 1.34. But due to resonance, the carbon-carbon bond length reduces to 1.39. Therefore, in benzene molecule, all the uh, no three bonds are equal. All the six bonds are equal with a bond length 1.39 angstroms. Now let us, the last topic of this bond length is the applications of the bond length. The determination, it helps in determining the structure of the molecule. It helps in the determination of the stability of the compounds. We all know that stability or reactivity of compound by knowing the bond length, but it may be changed due to resonance, hybridization, or presence of lone pair of electrons, etc. So students, now let us discuss the next bond parameter. The next bond parameter is bond angle. Bond angle, you know, it is the internal angle between the orbitals having bonded pair of electrons. Bonded pair of electrons, not the lone pairs of electrons, in the valence shell of the central atom in a molecule. For example, this is the example of water. This is oxygen, this one is hydrogen, this is also hydrogen. This is oxygen hydrogen bond pair, this is oxygen hydrogen bond pair. The internal angle between this oxygen hydrogen bond pair is 104.5, and this is bond angle. Here we have lone pairs of electrons also, but that is not considered as the bond angle. The bond angle is the internal angle between the bonded pair. This is one bond pair of electron, this is another bond pair of electron. This internal angle between the two bond pairs of electrons is known as bond angle. Like in water, it is 104.5 degree, in ammonia it is 107, and in methane it is 109.5 degrees. Now let us discuss the various factors that affects the bond angle. The very first factor is the hybridization. Hybridization, you all know, there are in organic chemistry, generally we discuss sp3, sp2, sp hybridization, and the S character of these hybrid orbitals affect the various bond parameters. Similarly, here also the S character of hybrid orbital affects the bond angle. As this in S character increases, the bond angle also increases. In the simplest example is alkane, alkene, and alkyne. Alkanes have single bond, they have sp3 hybridization. Alkenes have double bond, they have sp hybridization. sp2 hybridization. And alkynes, they have triple bond and sp hybridization. In sp3 hybridization, the bond angle is 190 degrees 28 minutes. sp2 it is 120 and sp it is 180. So as the S character is increasing from sp3 to sp, the bond percentage S character increases from 25% to 50%. As the S character is increasing, bond angle increases from 109 degrees 28 minutes to 120 to 180 degrees. And if we see, there are compounds in which, like in instead of water we have H2S, the group of atom or atom changes, other atom or group of atom changes, then the bond angle will vary, but to a small extent only. So the next factor that affects bond angle is the presence of lone pair of electrons. There are many examples in which central atom exhibit particular hybridization, even then bond angle differs due to the presence of lone pair of electrons. For example, water, ammonia, and methane. Methane, ammonia, water. All these three molecules have sp3 hybridization. Due to sp3 hybridization, their bond angle should be 109.5 degrees or 109 degrees 28 minutes. but in methane it is 109.5. In ammonia it reduces to 107, and in water it is 104.5 degrees. The difference in bond angle in spite of sp3 hybridization is due to the presence of lone pair. In methane there is no lone pair of electron. In ammonia there is one lone pair of electron, and in water there are two lone pairs of electrons. As the number of lone pairs of electrons increases, the bond angle decreases, and this is due to the Whisper theory. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. In water there is lone pair repulsion is greater, the bond angle reduces to 104.5 degrees. In ammonia there is lone pair bond pair of repulsion, therefore the bond angle is 107, and in methane there is only bond pair repulsions. The next factor that affects the bond angle is the electronegativity of atom. Electronegativity of atom: if the central atom is surrounded by same type of atom, then electronegativity of the central atom decreases, bond angle decreases. Here ammonia and PH3 phosphine both belongs, nitrogen and phosphorus both belongs to the 15th group of the periodic table or 5th group of the periodic table. Among nitrogen and phosphorus, nitrogen is more electronegative, phosphorus is less electronegative. Due to less electronegative nature, the outer central atoms are different, but hydrogen are common in both the molecules. In ammonia, the bond angle is 107 degree. In phosphorus, it is pH3, it is 93 degrees. The difference is number of lone pairs are the same. The difference is in the electronegativity. Nitrogen is more electronegative, so the bond angle is greater. And in phosphorus, electronegativity is less, the bond angle is reduces. So electronegativity of central atom decreases, bond angle decreases. Electronegativity decreases, bond angle decreases. Another example is of water and H2S. Oxygen and hydrogen, oxygen and sulfur both belong to the 16th group of the periodic table. Oxygen is more electronegative, sulfur comparatively sulfur is less electronegativity. Electronegativity decreases, bond angle decreases. Also decreases. The next factor that affects the bond angle is presence of multiple bonds, double or triple bond. If double or triple bond is present in a molecule, the bond angle is lower than the expected value on the basis of the geometry of the molecule. Geometry is very important. Geometry depends upon the type of hybridization. So the presence of double or triple bond affects the bond angle. Let us take the example of this is two molecules, CF2O and CCl2O molecule. They have sp2 hybridization. The geometry is trigonal, planar triangular geometry. Carbon double bond O, here also carbon double bond O. Here it is carbon single bond F, fluorine, carbon single bond fluorine. But in this molecule, carbon single bond chlorine, carbon single bond chlorine. So the presence of multiple bonds here, the bond angle between CO and CF, it has increased to 124, but carbon fluorine bond angle, FCF bond angle, that reduces to 108 because of the repulsion that is offered by the pi electrons. The two bonds the two CF bonds come closer to each other, but chlorine is bit less electronegative. Here again the CO-Cl bond, it is 124, but Cl-C-Cl bond, that is reduced to, from 120 it is reduced to 111. Similarly here, tetrahedral molecule sp3 hybridization, the angle should be 109 degrees 28 minutes or 109.5 degrees. Here also, due to the presence of double bond, you can see the bond angle that has reduced. Here it is reduced to 102.5, here it is reduced to 103.5, here it is 108, and so on. Hello. The next bond parameter that we are going to discuss now is the bond energy. Bond energy of a molecule A2 or AB molecule, it may be defined as the amount of energy required to break up 1 mole of chemical bonds in the gaseous state into gaseous atom. Gaseous state into gaseous atom, 1 mole of chemical bonds. For example, here we have taken A2 or AB for reference. This A2 is a gaseous molecule that breaks into atom A, 2 atoms of A which are in the gaseous state. In this reaction, X kilojoules per mole of energy is required. So this is a positive value, that means this amount of energy is absorbed, and this X kilojoules per mole of energy that is absorbed is the bond energy. If it is a heteroatomic molecule like AB, in the gaseous state, it ionizes, it breaks into the bond, AB bond breaks into and forms a gaseous atom A and a gaseous atom B. In the breaking of this bond, Y kilojoules per mole of energy is required. This energy, which Y kilojoules per mole of energy, which is required to break this AB bond, is known as the bond energy. So we can define bond energy as the amount of energy released. We may also, this is another definition, the amount of energy released when 2 atoms in the gaseous state combine to form the gaseous molecule. It is just the reverse. Here the molecule, the bond is broken, and in another way the bond is established. Like a gaseous atom combines to form combines with another A atom in the gaseous state to form molecule A2 in the gaseous state. Here bond is established. Whenever a bond is formed, the energy is released, and here minus X kilojoules per mole of energy, minus indicates the release, X kilojoules per mole of energy is released. Here when the bond was broken, X kilojoules per mole of energy was consumed. Suppose A gaseous atom combines with B gaseous atom to form molecule AB in the gaseous state. Bond is established, energy is released. Y kilojoules per mole of energy is released. This energy released is known as bond energy. So bond energy can be defined in 2 different ways: energy required or amount of energy released. Energy required to break up 1 mole of chemical bonds. Energy released when 2 atoms in gaseous state combine to form the gaseous molecule. The only difference is in absorption and release of energy. In the case of molecules of the type ABN, it is a polyatomic molecule ABN. In this case, average bond energy is the term which is used. For example, water, H2S, NH3. These are some of the examples we can discuss. So in case of polyatomic molecules, it is the atomization energy of the molecule. Atomization, the energy which is required to break the molecule into atoms. Atomization, to bring molecule in the atomic form by breaking all the bonds, divided by the total number of bonds present in the molecule. Atomization energy of the molecule divided by the total number of bonds present in the molecule. So mathematically we can write like this: average bond energy of AB bond in ABN molecule, average bond energy of AB bond in ABN molecule, total dissociation bond energy of ABN upon total number of bonds in ABN. For example, water, it has two OH bond. One is this one, other is this one in the gaseous state. So first one of the bond will break. Suppose this bond breaks. So this hydrogen atom comes in the gaseous state and this bond remains intact, HOH, in the gaseous state. And in this step the energy consumed is 500.8 kilojoules plus energy absorbed. Now in the second step, this second bond, HO bond, which was intact in the gaseous state, it breaks. It forms hydrogen atom in the gaseous form and oxygen atom in the gaseous form. In this step, 424.7 kilojoules per mole of energy is required. We sum up these two and the reaction is H, water molecule in the gaseous state, gives two hydrogen atom and an oxygen atom in the gaseous state, and the total enthalpy change, the total heat absorbed, the total energy absorbed is 925.5 kilojoules per mole. So this is the bond dissociation energy or dissociation bond energy. This is the total total energy of the molecule. So the average bond energy of OH bond, HO bond or OH bond, it is this total energy divided by 2, because there are two OH, HO or OH bonds. So it is divided by 2. It comes out to be 462.5 kilojoules per mole. So in this table, these are some of the values to understand bond energy better, and you can go through them and correlate bond energy with the bonds. Now let us discuss the salient features of bond energy. The bond energy of sigma bond is greater than that of the pi bond. We all know that sigma bond is a stronger bond because of the greater overlapping, head-on overlapping of the orbitals, and pi bond is a weak bond. So naturally a strong bond will require greater energy to break down, or the bond energy of sigma bond is greater. Bond energy increases as the number of bonds, bond order increases. Naturally, as the number of bonds increases, bond order increases, or number of bonds increases, the bond becomes stronger and more of energy will be required. So carbon single bond carbon, bond energy is lesser than carbon double bond carbon, which is lesser than carbon triple bond carbon. Similarly, bond energy of carbon nitrogen bond, single bond is lesser than carbon double bond nitrogen as in cyanides, and is lesser than carbon triple bond nitrogen. The third salient feature of bond energy is that it increases as the contribution of p orbital increases in the hybrid orbitals. So bond energy of sp3 orbital is greater than sp2 orbital. sp3 orbital is greater than sp2 orbital, and of sp2 orbital is greater than the sp orbital. And sp3 orbitals, they generally form the sigma bonds. The bond energy decreases as the number of lone pair of electrons increases. Carbon single bond carbon, there is no lone pair. The bond energy is 347.3 kilojoules per mole. Nitrogen, having one lone pair of electron, nitrogen single bond nitrogen, both the nitrogen having one lone pair of electron, the bond energy is 163.2 kilojoules per mole. And oxygen single bond oxygen, having two lone pairs of electron, each oxygen atom having two lone pairs of electron, the bond energy is 146.4. So here we can see that oxygen having two lone pairs of electrons, each oxygen having two lone pairs of electrons, the bond energy is less. And carbon single bond carbon having no lone pair of electron, the bond energy is more. So bond energy decreases as the number of lone pair of electrons increases. This is because this lone pair of electrons, presence of lone pair of electrons increases the electrostatic repulsion. The electrostatic repulsion between the lone pairs of electrons between the bonded atoms increases, and that weakens the bond. Within a group, if we see the bond energy decreases from top to bottom in the group, because as we move down from top to bottom in a group, size of the atom increases, so naturally the bond length will increase. Bond length will increase, the bond energy will decrease, the bond will become weaker. Cl, single bond Cl, chlorine, the bond energy is greater than bromine, single bond bromine, which is greater than iodine, single bond iodine. Similarly, these examples, this is the first group, hydrogen, lithium, sodium, potassium, and these are the halogen acids. And this is why the bond energy decreases from top to bottom. This is due to increase in the bond length. In short, the parameters of the bond depends upon the structural environment of the bond. Now let us see the applications of this bond energy. Although many information can be drawn from the bond energy data, but here we have discussed three facts. First is determination of the relative electronegativity of the atom. Relative electronegativity of atoms we can guess or we can mathematically calculate. Let us see the example. Bond energy of carbon, single bond carbon, is 347.2 kilojoules per mole. Hydrogen, single bond hydrogen, it is 436 kilojoules per mole. The bond energy of carbon hydrogen bond, it should be the average of these two, 347.2 and 436, that is 391.6 kilojoules per mole. Assuming that carbon hydrogen bond is purely covalent, as in carbon 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 hydrogen bond, this average will be when we say that carbon hydrogen bond is purely covalent. But actually the bond energy of carbon hydrogen bond is 413.4 kilojoules per mole, greater than 390. The average what we were expecting, because we were expecting on the basis of pure covalency of carbon hydrogen bond, that is higher than expected value. In other words, there is difference in that. This difference in the expected value and the observed value is due to the difference in the electronegativity. This difference in energy will give out the electronegativity difference of the two atoms, that is carbon and hydrogen. From the value of bond energies, we can also find out the mechanism of the reaction. In certain cases, mechanism of the reaction may be known by bond energy. Here we consider the mechanism of halogenation. CH4, halogenation of methane. Methane is CH4 plus X2 gives CH3X plus HX. So this is methane which combines with chlorine. This is the methyl free radical that combines with chlorine to form this HX plus chlorine atom plus this methyl free radical. This is a slow reaction. Now this methyl free radical formed combines with chlorine atom. This is a chlorine atom, this is a chlorine free radical. With chlorine free radical, this free radical combines with this free radical to form CH3X. This is a fast reaction. The formation of free radicals, it is a slow reaction. So from this we can also make out the mechanism. From the bond energies, the values of bond energies, we can make out the mechanism of the reaction also. The third parameter which I told we will consider is the calculation of the heat of reaction. Heat of the reaction can also be known from the bond energies. Let us consider hydrogenation of 1-butene. This is 1-butene. Hydrogenation is the addition of hydrogen. Hydrogen will be added at this double bond. So when this carbon double bond carbon bond energy hydrogen is added, the molecule became butane. 1-butene on hydrogenation forms butane. So what is done? This one of the carbon bond is broken and 2 carbon hydrogen bonds are established. When hydrogen is added, one of the hydrogen will get added at this carbon. CH bond is established, so it becomes CH2. Another hydrogen atom get added at this carbon and it forms CH3. So energy, if we see hydrogen, this hydrogen atom molecule will have to be broken down. For this hydrogen to change into the hydrogen atom, atomization of hydrogen molecule, 436.6 kilojoules of energy, 436 kilojoules of energy is required, and to break this double bond, 606.7 kilojoules per mole of energy is required. Thus, the total energy required to break the bonds is 1042.7 kilojoules per mole of energy. The energy released in the formation of bonds. Which bonds are established? Carbon, here carbon hydrogen bonds are established and a single bond carbon, single bond carbon is formed. Here carbon double bond carbon was broken down and this bond was broken down. Now a single bond is established and these 2 hydrogen atoms get added. So carbon, the energy released in the formation is carbon single bond carbon, 347.3 kilojoules of energy will be released, and in forming 2 CH bonds, 2 into 415.5 kilojoules. So total energy released is 831 kilojoules, 831 in the formation of 2 CH bonds. Thus the total energy released 347 in forming carbon single bond carbon and 831 in forming 2 carbon hydrogen bonds. The total energy released is 1178.3 kilojoules per mole. So this is the energy released and this is the energy which is consumed. So the net energy is 1042.7 minus 1178.3. This is minus 135.6 kilojoules of energy. So this energy is released 135.6 kilojoules per mole. Energy released is greater, energy consumed is less. So this energy is released during the hydrogenation of 1-butene to butane. Thus heat of hydrogenation of 1-butene is 135.6 kilojoules per mole, while the experimental value determined is 126.8 kilojoules per mole. These two values are quite close to each other. We have done with the bond parameters, and these are the references which I have taken into account during the these slides, and you can to go in details further, you can consult these books and go through the topics in these books. Thank you very much.